Dynamic traffic patterns of a production application. So a lot of this is kind of subjective to like the traffic pattern of an application. Like they differ, all of them differ. Some are very dynamic, some are very static, some differ depending on the day. So most of the way I'm thinking about this is in our own context and ship's context or context that I've seen before. So if you see something that doesn't necessarily make sense for your use case, I'd love to hear about it. The rest of the group would too. So feel free to interject anytime, ask questions, any of that. So okay, first we're going to talk about what Elastic Container Service is. So basically a container management service that runs on top of EC2, AWS EC2. So you could call it container orchestration. It doesn't do all of the cool flashy things that like some of the more robust orchestration services do, like Kubernetes or Mesos or something like that. But it does a pretty good job for kind of what it is. It's extremely easy to set up. It's somewhat well documented, as all AWS services are, and it's fully managed. So you have you're not managing a bunch of kind of boilerplate, not boilerplate, but infrastructure to help you run containers on AWS. So. Like I said, it runs on top of the EC2 service, so it uses EC2 instances as container hosts. They run an ECS agent, so it's just a little daemon process on the EC2 instance that communicates with the ECS API. What that basically allows it to register, deregister containers on the instance with your cluster, and provides logging and certain things like that from the actual container host. The way AWS or ECS kind of described, oh man, I'm missing a quote. Sorry about that. The way it kind of thinks about containers is in what they call a task. So each task is basically made up of one or more containers that is described in a container definition and task definition, which we'll get to in a minute. That's basically where you tell ECS how to run your container or group of containers. And then you can either run one-off tasks on your ECS cluster, or you can run what they call a service, and it's basically just a managed task. It will provide things like auto scaling, which we're going to talk about today, process management, so what happens if it dies, and general kind of process management features for your task. Okay, for demonstration, we took one of Ship's microservices and kind of packaged it up in this generic thing we're calling Super Awesome Demo Service. It is running as an ECS cluster. It's on the container host we're using, or ECS optimized Linux. Basically, that just gives us the ECS agent and Docker. So you can really run any flavor of Linux you want as an ECS container host, as long as you install the ECS agent and run Docker. So it's pretty flexible. The service is an API. It's written in Go, and then it uses Elasticache Redis for kind of a read from cache. So pretty simple. This is the architecture. We're using the application load balancer in front of the ECS cluster. So we're doing some dynamic port mapping and things like that from the container host to the target group. So we're not going to get too far into that, but just kind of some detail on how it's hosted. So here's what AWS calls a container definition. Container definitions are basically how you tell ECS what to run. So it's going to include your Docker image, which you can pull from anywhere. You can pull it from like Docker Hub or the Docker Store, or you can pull it from Amazon's ECR, Elastic Container Repository, or Elastic Container what? Registry, yeah. So basically like just hosts Docker images. So you can set limits for each container. So you can set CPU limits, you can set memory limits. You can also override commands from a Docker image. So say you have one image that is being used in multiple different kind of facets. You can run different commands depending on the implementation or depending on the purpose of the container. And there's a few other options that I didn't really think were relevant. And since each service or each task can contain multiple containers, you have a flag they call essential, and this is basically kind of the main container in the group of containers. This is the one that if it's not there, the task will die. So you can actually have containers inside of a task or in a task that could die, and the task will keep running. So there's a little more kind of implementation detail, but if there's only one container in the task, it's always essential because it's literally the only thing it can monitor. And then they have what they call a family, which is kind of like a group of task definitions. And you basically, anytime you update it, you create a revision in the family. So I will explain a little bit about that in a minute. Here's a task definition. Task definitions, like I said, is a way to describe how to run a task or set of container or a set of containers. These tasks can run with IAM roles, so it gives you access to a bunch of basically all the features of IAM without having to use like a console user or a programmatic user and give a access token access to all sorts of different services. So it's a lot more secure. It auto rotates credentials and things like that. You have kind of a network mode. There are different types of network modes. We won't get too far into that, but we're using the bridge network. So Docker Bridge Network is kind of the default there. You can do some interesting things with associating different tasks to network interfaces through the networking mode, but I would recommend reading up on it. It's cool, but not really important here. So there's your container definitions as well. You can mount volumes just like you can to any Docker container. You have placement constraints. I don't know what requires compatibility is, but then you also have task level CPU and memory limits. So this would be like if your group of containers exceeds a certain limit, then do something. We're not going to use these. I think this is mostly used for Fargate, or if you're running like complex tasks with multiple containers. We're doing neither, so we're going to set all of our limits at a container level. So one of the first things when we think about scaling an application is you really have to know a lot about the application you're about to scale. So for instance, you need to know kind of where you think the bottleneck for a service might be, because it's going to be really important to watch kind of metrics on those kind of areas of your application to be able to make sure you're scaling on the right metric. So some of the popular ones are CPU, if you're hitting CPU limits, memory limits, and then concurrency limits, which this one's a little interesting. I couldn't really find a great way to explain or name this one, but this would be kind of like internal concurrency limits to an application. So like in like the context of Go, they have a concept of like max processes per Go application. They call it Go max procs, I think. And it's just basically a concurrency tuner, I guess, inside of Go. So that would be like if you have that set too low, you might hit a concurrency limit where you can't spin up enough basically processes or threads to handle the incoming traffic. So you have to know when to scale. So depending on your traffic patterns, you could say, I generally have a traffic increase that's slow, lasts a few hours. Then you could probably set your scaling, kind of the points of each scale later. Like so you could set your CPU limit higher, or not your limit, but where you scale on CPU higher, because you know that it will take longer to reach that point. You can, if you have very bursty traffic patterns, you would want to set it lower because you want to scale as quickly as possible when you need to scale. So you basically use the same kind of bottlenecks to determine when you need to scale as well. And then also what's really important is kind of performance and load budgets. You need to know what kind of mark you need to meet. So at Shipped, we have a 20 millisecond performance budget on all of our backend services that are written in Go, just because it's a fast application. We also write a lot of Ruby on Rails, so those limits or those performance budgets are a lot higher because Rails is inherently slower. But you need to know kind of your performance budget for your application so that you know, well, if it can handle 50,000 requests per minute, but around 30,000 requests per minute, my P99 response time is 100 milliseconds, then that's obviously not okay, and you need to scale earlier. So load budgets are also like the kind of load you expect the application to do in production. So we could load test everything at 250,000 requests per minute if we wanted to, but sometimes that's not really reasonable. We don't need to spend the money to be able to scale to that level. So just knowing what kind of load your application needs to handle is important. Okay, so here's kind of our strategy for finding kind of the resource and concurrency limits of our application. So we're going to start with one container. You can do it differently. This is the path I like to take because the math is a lot simpler. You're going to start with one container, and then you're going to set reasonable soft limits. So you want to be able to exceed your limits, and they need to be reasonable. They actually don't really matter what they are because you're running one container. So as long as the host you're using can handle more than one container, you're generally fine. And as long as you're using soft limits, so you can exceed those limits and then kind of see where it bottlenecks and then tune them appropriately later. You need to be able to graph what you're doing. You need limit metrics. So you need so say we are mostly monitoring CPU and memory. We want to graph those metrics so we can watch them as we load test. And then you want to graph the performance metrics. So server side metrics are great. That's actually kind of the best kind of performance metric in my opinion. You can also do kind of client side, wherever that client is. If it's outside the network, inside the network, you obviously open yourself up to kind of other bottlenecks that you might not necessarily be measuring. But generally it's, as long as you're in the same network as the thing that you're load testing, you're generally fine. So you want to have visibility into what you're doing, basically. So the next thing we're going to do after we make sure we can do those two things, we're just going to send load to it. So we're not going to we will show you kind of our architecture for doing this. There's a lot of different patterns. It doesn't really matter which one you use. So you're going to just want to be able to send load to your application. And then we'll adjust container limits if appropriate. I actually already knew a lot about this application, so we're not going to actually adjust the limits, but we'll show you kind of how we found them. And like I said, the limits don't matter initially because you're running one container, so you're not having to do the math on, or you're not having multiple containers compete for resources. So if you go over, it's fine. And one key thing here to note is that we're going to use realistic traffic patterns. So if we know that this application will see a gradual increase in traffic over the day, then we'll do something like that to warm the infrastructure up, make sure that it can handle a gradual increase in traffic. If it's say you're having like a launch or something, you want to make sure that it can handle a kind of an abrupt elevation in traffic. So you just want to make sure you're tuning for the specific use case. There's a lot of different ways to do that, but that's really important. So, okay, so we're going to find some limits. First, we're going to do some math. We're going to kind of note some important metrics. So the metrics I'm going to be watching are the cluster CPU utilization. So I'm using one container again. This metric is defined as the total number of CPU units we're using times 100 divided by the total number of CPU units available to the cluster. So this is kind of what your container is using versus what the cluster can offer that container. Memory is kind of the same thing, what the container is using oh man, did I do 10? That's 100, sorry, that's 100, not 10. And then divided by the total memory available. Those are pretty simple. They also offer metrics for the service CPU and service memory utilization. So for the actual service you're running, those are a little bit more those are a little harder to monitor. AWS kind of shows them in several different places and they don't really correlate to each other. It's kind of weird. I would not trust most of the metrics. They put them in kind of weird places too. So I would rely on your own tools to kind of measure or CloudWatch is fine. But if they show you a graph on, say, the scaling policy page, I would make sure you can correlate that to another graph that makes sense. The service, so they have service versions of each of these metrics. Service CPU utilization would be the number of CPU units you're using times 100 divided by the CPU units reserved by that service. So say you're reserving 256 CPU units and you're using 20, you're going to be about 10% CPU service utilization, and same thing for memory. So it actually accounts for what you're reserving at the container level. So this is a little bit of math on what we're doing here. So I'm setting my first CPU limit at 256 CPU units. We're using M4 2X larges, so they have 8 virtual CPUs, and so that's 8,192 total CPU units divided by 256 CPU units per container per our limit, and it's going to put us at 32 containers per instance, and that's kind of max load. So I'll kind of explain why that can differ and why you probably don't want to run 100% all the time. But for our purposes here, the metric we're watching is 3.1% of the cluster CPU. So basically, I found that by dividing 1 by 32. So I want to make sure that my one container is not using more than 3.1% of the total CPU. So obviously this math can change depending on the unit, or the limits you're setting, and the instance size you're running, the instance class you're running. So same thing for memory. I kind of know this application is not memory bound, but if it were, I would do the same math. So I'm setting my memory limit at 256 megabytes. I'm using this same instance size. So it has 32 gigs of memory, so 32,768 divided by 256, which is my limit, and I get 128 containers per instance total. This is kind of at some level a bin packing algorithm, because you want to make sure, basically the concept of bin packing is fitting the most things into the smallest amount of boxes. So this is exactly what we're doing here. We're fitting the most containers onto the smallest number of instances possible. So we're going to start out with kind of a lower level of load. So I kind of cheat. I know this application really well, so I knew kind of where to start, but it's not a bad idea to start low and work your way up. It's really just kind of a guessing game at this point to find where to start. So the metrics I have here are response time. This is actually not server side. This is from an instance in the same network as the service. So they're relatively accurate. I have the min and the P99. If you're not familiar with P99, that's basically 99% of the responses are going to be under less than or equal to this metric right here. So we're leaving a little room for outliers. As you can see, there are kind of some spikes on the response time graph, but the 99% of our responses are 20 milliseconds or less. So I'm using the CPU, cluster CPU from CloudWatch, and the service memory, actually that's cluster memory, I'm sorry, from CloudWatch as well. So at 2100 requests per minute, over 4 minutes, I'll see that I kind of am guessing that it's CPU bound. So we're at 2.5%. And remember, our goal is 3.1%. That's our limit. So I step it up to 2,400 requests per minute, and I'm getting closer. I'm about 2.8% of the cluster CPU utilization. And then I bump it up to 2,700 requests per minute. And here is where I'll put my thing in there. Sorry, you can see it though. It's 3.2-ish. So I think we're technically over at this point. So I go ahead and bump it up a little more just to make sure at 3,000 requests per minute for one container, we are at 3.6-ish percent CPU utilization for the cluster. So we can tell we're definitely not memory bound. I don't even know what that number is, but it's very, very small. So, and then one thing to make sure our P99, we're kind of in the ballpark of our performance budget. So it's not like 100 milliseconds. So we're done load testing at this point because we've found kind of the concurrency limit for our CPU limit. So now we're going to set up an auto scaling policy. So for ECS auto scaling, there are a couple of different types of scaling. We're only going to really kind of explore one today. That's target tracking. This is kind of basically finding a target and then trying to stay as close to that target as possible. So there's also the option for step scaling, which is kind of, I think of it as kind of like a shotgun approach. Like every so often, you're going to check to see where you are. If you're not where you need to be, you add like a larger number of resources, basically containers, to the thing, and reevaluate in another period of time. So for a more dynamic traffic pattern, target tracking makes sense. So for target tracking, you can choose 3 different metrics to scale on. You can choose CPU utilization, memory utilization, or kind of an RPM per target type metric. So we're actually going to choose that because it kind of makes the most sense for our use case. It makes the most sense in my head. I know that at 2,500 RPM, I need to start scaling. I don't really want to do a lot of math on CPU for figuring out where I'm going to scale, and requests per minute is a great kind of business metric for kind of measuring throughput of an application. So our RPM per target metric, so we're going to start scaling at 2,500 requests per minute. They also have the concept of like scale out cooldown and scale in cooldown. So say we're going to check as soon as we hit 2,500 requests per minute, we're going to scale to another container, or we're going to add another container. Then we're going to wait 30 seconds before we do anything else. So this keeps you from going from, if you have a if you have a big spike in traffic or something, it just keeps you from kind of flapping around where you need to be. So for more bursty patterns, you're going to want to keep that cooldown lower, and then for more kind of static patterns, you're going to want to keep that cooldown higher. Same thing with scale in. So say our traffic decreases, we're going to remove containers every 30 seconds ish. So we've set that on the cluster that we're using. We actually have been running a load test on it since we started, and Wesley's going to come talk about that test and kind of some load testing architecture. So,
I luckily do not have a lapel, so good enough. All right, so I'm Wesley Brown, DevOps engineer at Shipped. I helped push a lot of the original auto scaling stuff. So, I'm going the wrong way. Which way am I going? Gotcha.
Yep.
All right, so we started a very large load test when we first got here. And we crashed our service, apparently. So, what happened here, we can go over kind of a post-mortem right quick like, is we had ramped far too high too quickly. So between potentially having 0 traffic and about 10, maybe 20 minutes, we had gone up to about 250,000 requests per minute. I'm sorry, about 180,000 requests per minute, peaking at around 250,000. And then we brought it back down. What we had kind of hoped to see in this situation is the service would have started off in a smaller amount of running containers, would have started taking more and more load. That would have set request count per target metrics higher as more requests started coming in. That would have caused ECS to notice that there are more request counts. It would then spin up more containers. That would cause the overall request counts per target number to go down, which would then cause ECS to kind of flatline for a minute, and then more would come in and go out, etc. So we can go back a few hours and try to find another probably okay load test to look at here. So we can go back even more apparently. When was the last time we had a good run? So, yeah, we're on the right service. Yeah, I didn't have anything in that window. All right, so let's just go back and look at our bad example. We created this test using artillery. So within artillery, you create these YAML files, and within that YAML file, you define how you want to load test the application. So in this particular case, we ran this 30-minute YAML file. So here you can see at the very top here, we set a target. That target is our internal endpoint for the service. Define a test name. We give it an influx plugin host. That is where we're obviously sending in our metrics for this particular test. If you're not running a metrics database, you can ultimately just view these things through the logs that they generate. If you're running it locally, it'll show in your console logs. If you're running it like we are through Lambdas, it'll show in the CloudWatch logs for the Lambdas themselves. We have these phases defined where for about 20 minutes we go from 50 users to about 4,000 users, and that was clearly far too much. And then we sit there for about 180 seconds. And then every minute we start stepping down 300 users at a time until we get down to about 700 users. And then we sit there for about 180 seconds, and then we just stop the test. So what we kind of hope to see in this test run is we would have seen kind of what we saw here, where we had this nice ramp. It would have been a lot more smoother, because this is a good representation of something that probably isn't very realistic traffic pattern-wise. You would probably see something along this line happen over the course of 12 hours, not necessarily over the course of 20 minutes. So we would have seen a much more smoother upward ramp here. We would have got up to a more flat line, and then we just started sort of stepping down, kind of like you see down here. We can go and view our current demo service running containers. And we can see that it's currently running 20, which is our maximum amount of tasks that we have set up. Yes?
I think it was like 128.
Did you have it set up at 128? Is this the minimum now? Okay. Let's go view that. So within here we can go, well, you said the maximum to 20. So that's probably why it failed. Tell you what, let's go ahead and set that to scale again. So within here, this is the service auto scaling config within AWS console itself. You can clearly set a minimum, a desired, and a maximum. You just select an IAM role, and you create a policy, and this is part of the target tracking policy. So this makes it super easy. It creates the CloudWatch metrics on the back end. It creates the CloudWatch alarms on the back end. Pretty much just does all the hard work for you. And if you wanted to view like step scaling, you would have to go in here and either create a new alarm yourself or create an existing alarm. The plus side to that is you have a lot more things to select to scale from. So if for some reason you wanted to scale off of a database size in RDS, you can scale your EC2 instances based off of your database size in RDS if you create a CloudWatch alarm to do that. But target tracking in our case works fine. All right, so we're going to bump that to 128. We're going to save it, update it. What? Yeah. And we're going to go back in here. And I'm going to actually lower this initial ramp to, let's say 38. We're going to save. And I'm not a huge fan of the Mac keyboard.
Stops working.
Where did your escape key go? It's no longer a real key?
Caps lock. Caps lock.
Why?
Because I took my caps. My escape keys are
All right. So we wrote this nice little script. So we're using artillery. We're specifically using artillery serverless. And artillery serverless pretty much just abstracts creating Lambda instances that are themselves running artillery. So instead of us running a single server that runs a single artillery instance that can really only use a single CPU at a time, which limits our number of users we can send, usually on this instance, for example, to around 400 or so users. We can run all of these in Lambdas, multiple Lambdas, and that allows us to run as many users as we can possibly run. It just spins up more Lambdas. So let's see, load test underscore 30. Super simple, it's a Node.js package. We pretty much just run the serverless SLArt. We pass it a base configuration. And from there, we just run the serverless deploy command and pass in the YAML that we configured earlier. So let's kick that off. And then as this goes, right now it's essentially packaging the entire directory that this is in, the home directory, so all the files you see above there, most of those aren't going to be used, but they're there. It's going to pack them into a zip. It's going to take that zip, it's going to send it up to S3, then it's going to create a CloudFormation deployment, and that CloudFormation deployment is going to take that zip file, create a Lambda service with it, and just kind of tell it to go. So as it works on that, we can go back over to here and pretty much just kind of wait on it to show up here. Eventually we'll start seeing some traffic come in on the side. We can also go into CloudWatch and view the actual logs like I was mentioning earlier. But I think what will be best off doing is just waiting on it. So I guess since we're pretty close to just, because this is going to start a 30-minute test, and I don't think we want to sit here and wait 30 minutes. We can check in on it later on down the line. Is there anyone who has any kind of questions on like artillery or any kind of questions on our actual auto scaling setup? Well, all right. Yo, man.
Do you allow
Can you say that again a little loud?
Could you elaborate a bit more on what artillery is?
Okay. Artillery is it's a Node.js package that essentially emulates users performing tasks. So we can go in here now that this is finished and view our YAML again. So at the very bottom down here, we have these scenarios, and this is what each user is going to do. So as it runs through, it's pretty much going to spin up a user. That user is going to do what we tell it to do, and then that user is just going to die. And then it's going to create another user and do the same thing. And it's going to keep doing that, and it's going to try to maintain whatever the amount of users we tell it to maintain. So in this case, we're creating essentially one request per user, and we're generating, let's say, 3,800 users per minute. That means we're on average sitting around 3,800 requests per minute. Huh? Is it per second? All right, sorry, per second. So, yeah, so outside of it just being a Node application, I didn't write much of it, so I don't know exactly how it works, to be honest.
I think it was written by Matt Nordstrom, right? After like the Nordstrom Matt. So it's pretty cool. Little command line, cool.
No? So, is there anything else? Went too far.
I got a little more, so we can use that.
Sure, we'll go ahead and let this run, and I guess you can come back up. Hey, look, we're already getting metrics. And they're all.
Oh, good job, Ed. Ed's on top of it. All right, so what's missing? There's a little more you can do here, more than we did. I kind of ran out of time. So there's a whole concept under ECS for EC2 Auto Scaling. It's not necessarily required, and what I mean, it's a good idea to do it, but it's not necessarily required to scale an ECS cluster. You can just provision, like, so I talked about knowing your service. If you know you're never going to need more than 100,000 requests per minute, then you can provision the infrastructure to handle that and then scale across that infrastructure as needed. So it's a good idea to do it. We didn't get into it today, but I can kind of explain a little bit about it. So there's two ways ECS kind of interfaces with EC2. From like a CloudWatch perspective and scaling perspective, there's resource utilization. So you can say over, like this test would be a good one, over 30 minutes of this kind of traffic, you watch what it does to the actual EC2 auto scaling group, and say there was an average of 30% CPU across the instances when you need to scale, then you just scale on that metric. There's pretty simple ways to do that for resource utilization. You can also do resource reservation scaling. So when you spin up 10 containers, say they reserve a certain number of resources, that's your limit. Your limit is basically a reservation. So it's saying I need 256 megs of memory and 256 CPU units. You can scale off of what's reserved on the auto scaling group. So this is really good for when you're doing, like, if you're doing blue-green deployments with containers. So say you're going to spin up 100% of the containers, you need to run a new version of software. You'll run both of them on the cluster at the same time, and you'll kill the old ones after. Reservation is a good way to make sure you have the auto scaling group resources there when you need them. So reservation is a little trickier. I did not do it because it's really, one, I ran out of time, and two, it's really not a fun process in the console. There's just kind of a lot of weird, like, little nooks and crannies. You have to go create little things, and it's not as pretty as what we showed you. So I would recommend finding a great way to do that with CLI, but that's just my opinion. So let's see. So does anybody have any questions? We'll wait on that test. We can kind of chat and hang out and wait on that test to complete and check in on it in a minute. But does anybody have any questions? Is anybody using ECS right now? All right. Do y'all scale? Auto scale?
Yes, badly sometimes.
Us too. Is there? Do you see anything I missed?
No, and
Okay.
there's a couple of things that I need to look into.
Oh, okay. Cool.
Brought up.
Sergey.
Here you shown like one type of task, and it's like you like say, okay, I use this instance and I use like this task and this task need like this amount of memory, this amount of CPU. Just divide and say, okay, I can run like 100 containers in this like, and that's it. But what if you have like a bunch of different like services and they consist of like different tasks and it's like you know it's this amount of like resources, this amount of resources, and they like run together. They run together on the same EC2 instances, or they run together on different ones.
Right.
Different?
So I guess it's kind of up to preference. I would say that running them all on the same EC2 or ECS cluster would take more upfront work on determining how the applications work together on the underlying resources. I would definitely recommend EC2 Auto Scaling at that point because it would be really hard to kind of tell, especially if you're working with like applications that have higher resource limits. They're more dynamic and they can affect the underlying infrastructure in a much more drastic way.
But we ran into that we have some like certain instances and we have different like containers. And these containers they like bigger, smaller, and like a bigger one when it's especially when it's like deployed, it's whole like available. So then it's like it just needs more less than this. But at this time it is deployed to this instance like just like free.
It doesn't have the resources to take another container.
Yeah, so you know it would be easier if like different like containers or tasks, like different type of them goes to different like instances. And in this case, the like calculation of the like resources needed will be as simple as you show. But if they just like 10 different types goes together into the same instance and we don't like in the morning we run like one instance of every and that's fine. But then like we hit some load and like oops.
Yep. Yeah, it's definitely a challenge on your patience and I guess just how much time you spend actually, load testing, figuring out different use cases. Like this is a very, very simple service. There's several other different endpoints, but this one's the most often used, and it has a really low resource footprint. So at Shift, we run every service on a different ECS cluster, so different EC2 instances. I feel like it gives us the flexibility to tune this stuff really well for the actual service, and we don't have to do all of the kind of like how does service A affect service B. It's definitely possible, and a lot of people prefer to do that, but I would definitely agree that a different cluster is easier up front. Right.
And it's like, and here you can like define like this task run on this EC2 instances, this task is run on this EC2 instances, and you can, pick different types of instances, you can like scale them differently, and you can just keep the calculation of the needed like scale, like as simple as on this show, right?
Right. Yeah, and especially like for this instance, or for this application, we don't have to run M4 2x larges. We could probably get away with doing it cheaper. On like some T2 larges or even smaller instances, and then scale them really well and save some money. So, but yeah, really good point. That's like one of those probably heated debates in a lot of places is do you run everything on the same cluster? We've certainly had conversations about it. Do you run them on different clusters? So, good call out. So, do we have any other questions?
Can you show how you set up your code for memory on auto scaling?
Yeah, absolutely. So we'll go back to our service. We'll go to auto scaling, and we can set up another scaling policy here. We'll add a scaling policy. We'll do target tracking. And we'll do super awesome demo service. And then we'll just choose average memory utilization. I'm generally not a big fan of averages because they tend to be kind of miscommunicate what's going on, but there are only options here. So we will, that looks like it was a scaling event right there. That's pretty cool. We can go back to our slideshow and actually go back to what our, I'm gonna have to do some math. Okay, so this was where we said we probably need to scale. So that's at 0.08%. So we could scale it like 0.08% would probably be a good metric. I don't know if we'll ever hit it. Oh, sorry, I don't know what I'm doing. But we can definitely do 0.08. This is percentage. Or maybe even just like 1 or 0.1. I don't even know if you can do less than 1. And we'll be really kind of cautious about that because I've not tested this. So, but we'd basically save that. On applications that are more memory bound, like we run a lot of Ruby on Rails, those are definitely memory bound. It would be a better example, so I probably should have picked one of those, but it's really simple to add more scaling policies. So we could add another one for CPU. We're not using CPU yet, but we could where's my slideshow? Yeah. CPU is at I think our scaling metric was at 3.2% from the math we were doing. So we could do average CPU, 3.2.
I'd like to point out that I think you're confusing container or EC2 instance memory utilization. There's EC2 cluster and the service.
Yeah, that's right. I didn't do my math on the memory. Yeah, good call out.
It's going to be ECS service memory utilization.
That's right.
Inside of influx.
That's right.
EC2.
Yeah, so we have to translate what the 3.2 would. Yeah, okay, great call out. Yeah, okay, cool. That's a good point. It looks like we're kind of exceeding the CPU utilization there. Yeah, so Wesley's point was 3.2 would be like for the cluster, and so you have to kind of translate that to the service. So you would really have a range around like 70 or 80%, something like that, depending on your traffic pattern. Go ahead.
And we have access to this like memory metrics because every EC2 instance we run on this cluster has this EC2, ECS agent, right? This agent actually like delivers information to the control panel about the like memory utilization and everything, right?
Right, yeah, so these are actually from CloudWatch, these cluster metrics. So we can edit them and it's coming from CloudWatch gives you ECS service and cluster metrics. For some reason my service metrics weren't working, so I went with cluster.
But these are out of the box metrics, right?
Mm-hmm.
So like
right.
Because in EC2 instances like Autoscaling, you cannot like scale out of like memory utilization because by default, whatever you run, it doesn't have the agent. So if you have the agent, if you deliver that, you should do something.
Oh, I see what you're saying. So this is actually from not from the ECS agent. So ECS agent I don't think it reports metrics on containers. It might, but we don't use that. So this is actually from CloudWatch for the EC2 instance. So like if we were to go back over to EC2, and then we'll find our super awesome demo service. So like for monitoring on this instance, this is the metric we're using.
It's utilization, but memory is not here.
Oh, great point. Yeah.
EC2 doesn't have this, and you like operate with this like memory utilization. It means that you
Good
can
point.
get this information somewhere.
Hmm.
I can get it, but I have to install like
like collect D or something like that, or yeah. Okay, I got you. That's a good point. Do you know where that's going?
We installed the CloudWatch agent on the analyzer in ECS.
Oh, okay, so we are using the CloudWatch agent. Gotcha. I did not know that. Good call.
It's
though.
like EC2 instance that you use in the ECS, servers to run these containers, like tasks on that instance. By default, out of the box, it has this like CloudWatch agent that reports memory utilization probably, and probably this agent itself.
Right.
Because
Yeah.
It's like we're not touching them, we're not like logging with that instance, we're not like seeing that
Good.
instance at all. You just have regular tasks.
Good call. So I wonder if it does come from the ECS agent then. I'm not actually too sure. That's a good point though.
Something like out of the box.
Yeah, so it's not dependent on whether or not you install the CloudWatch agent.
So if you run some like application in the this container service, you have better out of the box control for the memory metrics, other than just if you run the same application in like EC2, Auto Scaling, for example.
Right. Yeah, that's a good point. Yeah, we tend to try to scale on requests per minute because I feel like it's more of like a synthetic metric. It's kind of what your user would be experiencing. It makes more sense from like a business perspective. So there definitely are use cases for scaling on CPU and memory for sure. Obviously, from like if it's not a web service, right? So if it's like a worker or like a asynchronous processing type thing, and you don't have HTTP traffic metrics to scale on, then CPU and memory would be a really good point. But yeah, that's a good call out. I had never thought of that. So. Cool. Does anybody have any other questions? Okay. Cool. Okay, so shameless plug time. If you like these things and you like turning this into this, then you should come work at Shipped because we're hiring. So, cool. Let's go look at our thing. See how it's doing. Uh-oh, we killed it again, I think. Do it?
It looks like we caught it right now.
Yep. Well, that did pretty good. It handled 125,000, 150,000 requests per minute before it really started choking.
If you go over to ECS,
Do it?
go over to ECS. So you can see the scale.
Oh, that's right. Yeah. Yeah, so we're running 41 containers. We're likely just not scaling quickly enough. So, yeah. So the point is, it's not easy. It takes a lot of time to dial and tune. I think we decided on these numbers 30 minutes before this meeting. So it takes a lot of time to dial and tune in kind of what you're scaling on, but it's definitely worth it. We've had our fair share of like elevated traffic events, you'd call them, and this has saved us many times. So cool. I think we're almost on time. Wow, cool. Well, thank you guys for coming. So I'll hang out. People from Shipped will hang out. Ed, I'm sure will hang out. So come find me if you have questions.